everyone. We're going to go ahead and get started. Thank you for joining us. In today's webinar, Ryan Vanderwerf will present an overview of the technology behind the GalecinoCar, which is an autonomous vehicle built using machine learning, Raspberry Pi 3, Groovy, Java, and our new microservice framework, Micronaut. So before we get started, I wanted to remind everyone that you're all muted at this time. So please make sure that you use the chat box to type any of your questions during today's presentation. And then we'll go ahead and host the live Q&A session at the very end. So we'll keep track of all those questions. And then if there's anything that doesn't get answered during that, we will take the questions down and follow up with folks after the webinar. And then also to remind everyone that we are recording the session today, and then we'll email all of the registrants within a couple of the days following the event. So sometime midweek next week. So with that, I'm going to go ahead and pass the controls over to Ryan and let him go into more detail.
Hello, everyone hear me okay?
Yes, you sound great.
Okay, great. Let's get started. So this is GalecinoCar. It does self-driving and remote control driving. So let's go ahead and get into it here. A little bit about myself. I'm a software engineer on the Grails Micronaut team at OCI. Got 2 kids, 6 and 13. If you need any help with Grails, Groovy, Micronaut support, any of that kind of stuff, let us know. And during the webinar or after in the chat window, and we'll have somebody help you. All right, so what I'm going to talk about today, I'm going to talk about the project itself, the hardware behind it, what you need to build your own, the software and how it all works, and then we're going to talk about the future plans that we have with the project. All right, so let's talk about a little bit about the project. These are some real-world applications for autonomous vehicles here. You got, a Tesla, an NVIDIA car, a Cadillac Super Cruise, and there's some other ones as well. So this is, all the real things you can do with these concepts. Obviously, this is a much shallower version of that, but taking these things to the next level is what real autonomous cars are doing today. And we'll show you a little bit about how some of this stuff works. Similar principles with the camera, so let's get into that. These are the cars that we built. My buddy Lee Fox and I had built all this stuff based on the DonkeyCar project. And these are the 2 cars we built, Vanderwerf 1 and 2. You can also see it right here in the background. Let's talk about the hardware. How do we make these things? So this is the chassis. You can buy this online. Sometimes Amazon has it in stock, but I've had good luck with this website, Nitro RCX. And they're about $100, sometimes a little bit less, to get one sent to you. So it's a pretty affordable car that's got standard servos and motors that you can communicate with via the a board here I'll show you in just a second. And it's 1/16 scale, so it's pretty small, but these things do go really fast. I think they can go upwards of 20 miles an hour. So that's pretty good for a car of this price. All right, so what we're doing for all the processing on it right now, we're using a Raspberry Pi 3B. It's just a 1.2 gigahertz quad-core ARM CPU. It's got a gigabyte of RAM, it's got a wireless adapter, and most importantly, it has a camera interface for a Raspberry Pi camera, which will show you how that makes the car work. This is the second most important piece besides the board in the car. I guess third most important is the servo motor driver. So it's a PCA 9685 servo board. It's got 16 channels, and it gives us 12-bit PWM servo control. What this does is gives us pulse width modulation. The Pi can't really put out, but this board can, and that's what makes the motors and servos work. So that gives you your throttle and steering of the car. Adafruit is the most common version. Those are really cheap. There's lots of knockoff ones you can buy on Amazon or anywhere else for about 12 bucks, so it's pretty affordable. The camera is also important. It's just a wide-angle Raspberry Pi camera. We use this for the self-driving mode, and we can also use it for remote control mode, so you can see what the car's doing, kind of like a rover type of deal. And that costs about $30. You do have to be very careful with these. We fried one of them at GreatConf EU just by picking it up, and someone hit it with a static charge. They're very sensitive, so keep that in mind if you build one of these and you're handling it. The other thing is we've got a battery here. So it's important to have a separate battery for the car versus the battery that runs the motors and servos on the car. And that's because those motors and servos draw a lot of current and can make the Raspberry Pi unstable if they're running on the same power source. So we found this is a really good sized candy bar portable charger that can put out 2.1 amps, which a lot of them can't do. We bought this on Amazon for about $20. We're really just zip tying that here along the bottom of the car. Show you here, and it's a really good size. A lot of them are weird sizes. They're either too big or too small, but that one just happens to fit perfectly in there, so you can not have to take it on and off all the time. And that, you know, it's about $20 on Amazon as well. Now the roll cage, we got these plans. They're based on the DonkeyCar, but these roll cages are 3D printed into 2 pieces. So there's a top part here, and then there's this bottom part that holds the board. And we basically take the chassis body top off of the RC car, and we put this on instead. So you can see the holes here in the main board are mounted on the strut towers of the suspension of the car, and then it just basically cotter pins that in so it stays in place. This also is really nice design because it angles the camera down 15 degrees, so it's looking down at the ground. And it mounts our Raspberry Pi board directly on it and our Servo board. So everything's kind of neatly tucked in there, and gives it some protection too when it crashes into things. So here's a link here you can get from the DonkeyCar site. I'll explain a little bit more about what that is in a little bit here, to print your own. If you don't have a 3D printer or your printer is too small, my friend Lee bought a printer to do this and then ended up being too small, so don't do that. You can also use a service online where they'll print these things for you and then ship them to you. Obviously, you'll pay a premium for that, but you won't have to have your own 3D printer to do it. All right, so to get this thing working, after we've got all the hardware put together, we need to do training. So if we want this thing to self-drive, it needs to learn and train to drive like a human would. So it's not as stressful as teen driving. This is my buddy Lee's son, Austin, who's learning to drive right now. That's much scarier in a real car with a teen driving it. So it's not quite that bad. But we need to also build a track. We can use simple masking tape that's white, as long as it's got good contrast against the background. And you can also build a center line. This track here has got a blue line. You can do a dotted yellow line, is which we did at GreatConf. So any of those will work. Here's a dotted line one here from one of the DonkeyCar events. And basically, the car is learning to drive and to stay between the white lines. Here's a track that my buddy Lee and his son built in their house for us to test all this stuff out. You can notice the cat there. The cat's actually gotten in the way. Talk about some of the future things we wanted to do with this. So things like cats don't cause crashes, things like that. All right, so a little bit about making a track. So the shape doesn't matter too much. You can do loop, figure eight, curves. You can't make too sharp of turns. What'll happen is the throttle isn't that great with the autonomous control as far as like finesse. So if it's too tight of a turn when you're training it, it can go off track. So you just want to make sure that those turns have enough wide turn radius to handle at a reasonable speed. Just make sure they're bright. Lighting is very important. I'll point out one thing at the very end when I've got a demo video where direct sunlight blinded the camera and the car just stops. So making sure that your lighting is good and not too dark, that could affect your training because it is looking at images of the car driving to learn. You can use a variety of materials, masking tape. One I'd like to use that I've seen is ribbon, so you can easily pull that up and down. If you use ribbon, you just need to tack it down with tape every foot or so, and then you can pull it back up really easy. It's a little bit more expensive than masking tape, but less labor intensive to put down and pull back up. Try to create 2 tracks if you can, if possible. The more you train it, the better it will learning, the better it'll handle different situations. So you might want to turn it around and train it too, going the opposite direction. If you're like a NASCAR driver and it's all left turns, then this isn't very interesting. So if you're doing an oval, try turning it around and see how it does going right. You may have to retrain it to go the other direction as well if it doesn't have enough learning data. So how we train the car is that we need manual control of the car. You can use the web UI controller. I'll show you a screenshot of that in a second. But one of the things that works the best is actually a PS3 game controller. If you use the PS3 controller, you have a lot more finesse and throttle, and you can also back up and slow down the throttle a lot better. And we ended up using that as a training mechanism at GreatConf this year to do training on site of the track that we built there. And you're just teaching it by example. So what's happening is you drive around 10 to 20 laps, and it'll record enough data to feed into the learning system. And basically what's happening is it's taking images of the car constantly, and it saves those. And along with that image, it's also taking car telemetry, which is the steering angle of the servo for steering, and then the throttle percentage as well. And so all of that goes in and to train the model via Keras and Tensorflow. And I'll talk a little bit about what those things are in a minute. So let's get into the software here. So we've got a bunch of components that we assembled this thing for. Really, the inspiration was to make something like DonkeyCar ported to the JVM. So we ended up using Micronaut as the framework to do the remote control driving around part. We're using a Java library called Robo4j to control the servos. And we're using Keras and TensorFlow to handle the AI of the self-driving mode. And then we're using DonkeyCar, which is basically Keras and TensorFlow. We're using bits of that under the covers in separate threads, which you can see in the code later, to control whether you're running manual control mode or self-driving mode. These are the software components kind of laid out of what all this thing's made out of. This is all running on the Raspberry Pi right now. So we've got Micronaut is our providing REST endpoints to a web UI for remote control. We're using the Robo4j library to control motors and servos when we're doing that manually, or remote control mode. And then we're using a library for the camera to take pictures as we go to see what you're doing called JR-PyCam. Those libraries in Robo4j, I'll talk a little bit about those more in a second. We also use a Python wrapper my buddy Lee Fox wrote called Galecino, Galecino.py. What that is it wraps just the self-driving parts of the DonkeyCar to get that going. And there's a reason why we had to do that, because of some limitations of TensorFlow and deep learning for J that are currently being worked on. All right, so let's talk a little about Micronaut. So what is Micronaut? So it's a modern JVM-based full-stack framework. We build modular, easily testable microservice applications. It's features built-in dependency injection, auto configuration, config sharing, HTTP routing, fast configuration, and load balancing, like client-side load balancing, I should say. It's got really fast startup time. It's around 1 second on a well-equipped developer machine. So somewhere in that ballpark, depending on how many features you've added to it. The cool part, though, is no matter how many bits of code you've added, because it uses compile time configuration of everything, even if you add more code to your project, it won't get slower and slower as the project grows. It'll always stay the same, because all of that work is done at compile time. We support Java, Groovy, and Kotlin. We're using mostly Groovy examples here for the remote control car part. We also have all kinds of support for distributed tracing with third-party tools like Zipkin. We've got a nice CLI that can generate code and give you a console. We've also got profile support, so you can create different kinds of projects for different kind of usage types you might have for Micronaut. So it really goes way beyond just what this simple car can do, but you could build a full-scale web application spread around on different, services. So we can also detect whether you're running on Google or Amazon and in the future Azure, so that it can gather data for you as the application starts to help you do load balancing and things like that. And also what's cool about Micronaut is it can not only act as a server, which was we're using in this case, but you can also use a client, or you can use it as a serverless wrapper framework. So you can make AWS Lambdas, for example, using Micronaut and have all the fun, cool bells and whistles that Micronaut gives you inside of serverless function. Because it starts so quickly, you don't take much of a hit on the performance on that end of it. So what does Micronaut have to do with an RC car? Well, because it starts so quickly, and it's so small memory-wise, it's a really good candidate to run on the Pi. Obviously, the Pi is no speed demon. It's pretty slow by standards compared to a regular PC. It doesn't have a ton of memory, but it's decent for a small thing. So we made this kind of ideal to try out on this. these are the guys that wrote Robo4j. They're Marcus Hurt and Miro Wagner. They're super helpful guys. So if you're ever building a robot project on the JVM, these are the guys to talk to. They're super helpful. If you contact them on Twitter, they also have a Slack community. You can ask for help building their own little framework. They also won a Duke's Choice Award, and it's robo4j.io. So we're using that for the motor types of controls. They actually have a whole framework you can use also for the Lego stuff. And that's actually the components here of Robo4j. So they actually have a core library, which is what we're using. They also have a SQL library, a math library, and then they have native libraries already compiled for you. So you're not having to compile JNI stuff. They have that done for the Raspberry Pi and the Lego Mindstorm EV3, which I've done some talks in the past for in workshops using a framework called LaJAWS. You can also use this framework to control motors and stuff like that. It's a little bit easier to deal with, I think. All right, so enter GalecinoCar. What is this? It's a horse breed developed in Mexico. It was brought from Spain by Hernan Cortez and other conquistadors. Picked this because it seemed a little bit nicer than a donkey, which is what we based this on. So what is this project? It's a port of DonkeyCar. It's a popular Python-based remote control car project. So my buddy Lee went to reInvent last year, came back, he's like, man, can you make something like this for the JVM? And I'm like, I think we can. So we gave it a shot, and this is kind of what we've come up with. And again, Micronaut's running as a remote control for the RC car. We also serve up a remote UI. We actually reuse the entire UI that DonkeyCar has on the HTML side of it. And Micronaut is acting like the Python code would and responding in exactly the same ways, so the UI will work. And we'll show you some code examples of that here in a little bit. And what the UI does is it lets you toggle between the TensorFlow Keras autopilot mode and the remote control mode. All right, so what is Keras? Some people here may be familiar with these kind of Keras TensorFlow types of systems for doing self-driving and autonomous learning. So I'll just kind of give you a really brief overview of what these things are in case you're not familiar with them. Keras helps you make a convolutional neural network, and it kind of gives you tools to do this in an easier way than just doing it at a lower level with TensorFlow, but really just a thing that sits on top of TensorFlow. What we're doing is we're taking convolutions, which are pictures of things and samples, and we're breaking those down into different convolutions and samples, all the way down until we get to finally an output, which is basically we're taking the input of learning a whole bunch of images and telemetry of driving, what our angle is of the servo, what our throttle position is, and we're turning that back down into output so that it can learn to drive at any given moment based on what it's seeing in the camera, which is two white lines, to either go left or go right and go forward or stop. And that's basically providing all of the guts of that. It's a 4-layer CNN, so they call convolutional neural network, that's handling all of this stuff. So earlier versions of it, I believe, did 3. But if you look at the DonkeyCar project code, and there's a file called keras.py, it gives you the actual guts of the model right there. And what is Keras? So really, it's just a high-level neural networks API. It's written in Python on top of TensorFlow. You can also use it with CNTK or Theano, other frameworks. It's basically teaching you to drive like a human. So you're basically giving it examples, and it's learning. So it's not like a reactionary thing like, oh, if I see this, do this. It's training based off of feeding it a whole bunch of data. And the more you give it, the better it gets. And so if you drive it around the track a minimum of 9 or 10 times, it can get it started scooting around. And the more you give it, the better. Our goal is to replace this with a framework called Deep Learning for J, which is a pure JVM framework that can actually import these Keras models in it. Because TensorFlow's Java support is a little bit lacking, they do have JNI support. However, their build tool, Bazel, doesn't seem to output 32-bit JNI libraries. It's I guess a shortcoming of it. And there's a ticket open for it as a feature request that was originally filed as a bug. I think it's a bug, but anyway, it doesn't do that. So we can't really use TensorFlow Java. Deep Learning for J has an issue currently with building on the Pi, but that's just about resolved, I think, now. So that would actually work on the Pi itself in a pure JVM fashion. So that's where we're kind of, I'll talk about that in the future parts of this, where we're going to take this after that. So once the model's trained, I control throttle and steering automatically. Sometimes the throttle's a little bit twitchy on this, so what sometimes you need to do is control the throttle manually and then let it do the steering. For whatever reason, it stutters a little bit sometimes. And the more training you give it, I've noticed, the better it gets. And it's all, you know, about lighting conditions and things like that. Here's the DonkeyCar side, so instructions for training. That's all the same stuff there. All right, so what is TensorFlow? TensorFlow is like the heart of the Google's project for AI. And it's a machine learning framework by Google. Keras runs on top of that. But Keras is providing basically pilots, which is, you know, a car implementation of that. And this is probably the most popular machine learning framework out there. The Java support is a bit lacking in 32-bit systems, especially on the ARM Pi platform. But projects like Deep Learning for J were made out of a need of the lack of support in that area that are kind of taking that torch forward. But you can create models for almost anything with machine learning. It's a really cool tool. You can do all kinds of things like chat, object recognition, touch, art, all these different kinds of things. I've got a friend of mine who has it hooked to his radar detector, and he's got CUDA cores in his trunk. And he's analyzing noise coming out of his radar detector while he's driving around with TensorFlow. So you could do almost anything with this stuff. You could do it on a farm. You could do it to check for predators and microphones, all kinds of stuff. Really, the sky's the limit. I found a really good list of interesting projects people have made with this, and I put the link here in the slides. It's really, really cool stuff. All right, so a little bit about DonkeyCar, which is what this was based off of. DonkeyCar is a Python project. GalecinoCar is really just a port of that. And because deep learning for J and TensorFlow, Jay and I really wasn't ready at the time that we made this, we've got kind of a hybrid thing going on here. The most promising one we'll go forward with is deep learning for J. And basically, you have to pre-train this thing beforehand. You can train it on your PC or on the car itself. It does take several hours. So once you've done your trial runs of training, to run the model through and make it learn, it takes a good amount of time, depending on whether you force it to go through all the data you have. You can anywhere from an hour and a half for 9 or 10 laps to 3+ hours. So that's something you have to do ahead of time. There's just not enough horsepower in a Raspberry Pi to do any of that kind of stuff in real time. The GalecinoCar bridge is just, you know, allows Micronaut to switch between remote control and self-driving modes. I've got some code snippets I'm going to show you here in just a second on that. So let's do some of the code here and see some Micronaut code. This is what the web UI looks like. If you notice, it looks almost identical to the DonkeyCar, if you're familiar with that. It's basically using all of the same HTML. It's just the endpoints that it's talking to on the car are powered by Micronaut. So a couple things to point out here. So you can pick a gamepad for training it. You can also do a tilt from a phone. That doesn't work very good, to be honest. And this is like a touch joystick here that you can drag your mouse up, left, up, down, right. Really not precise enough and a little too laggy to do for training. And here's a picture. This is, sorry, a blurry one, but this is in my friend's lab in the evening. And then here's this drop down here. And this is how we switch between user mode, which is remote control, or the autopilot mode. And then when you're in autopilot mode, you can start the vehicle and it'll start running the model at that point, or the car. All right, so let's look at a couple things. So here's a controller in Micronaut. This is kind of the first thing that the web UI I showed you hits. So what it does is it got a couple examples here. The first thing it does is initialize the car. Because it's using PWM motors with pulse width modulation, they have sort of safety settings built in where you have to give it a certain value first before the motors will respond. And that's kind of a safety mechanism, because otherwise what might happen is if you turn a car on, it might shoot off off your table or whatever. And if it's an airplane, then it would be even worse. It would crash, and those things are pretty expensive. So we do that first in there. We mark things with singleton here, and we mark that, annotate that as a controller. At this point, this is mapping to the root directory of the project. If you wanted to change this to be something else, you just put a different path here, and then it'll automatically do that. This post construct here is something that will run when the class is initialized. Transactional is not needed at all. I was messing around with some database stuff. So I had a vehicle object saved as an entity just for fun. It doesn't really need any needed in this case, but you can do transactional and do database stuff with it. That is entirely optional here. All right, so we've got another endpoint called take still. So as you're driving the car around from the UI back on those pictures, we call this thing called get me a video. And what it's doing is we're taking a still image using the JR PyCam library, and we're setting these headers here with Micronaut to tell it to set this value here. And this is actually a little bit outdated. If you look at the code link I sent you at the end, we had to make a little bit of change to this after one of the Micronaut releases. Next, the most important controller method is called drive. So when you're using the joypad on the web browser, it's calling drive, and it's basically giving it an angle and throttle value, and that is anything from -1 to a +1, 0 being stop or in the middle. And what driving mode we're in, so we can switch driving modes. Recording is used if you're doing training mode, in this case. So what we do is we just give it a drive schedule. We tell it what that point is in the joystick. And because this is called constantly, well, I'll show you in the code here, we're managing a queue so it doesn't overwhelm Micronaut with stuff in it. And we give a response here. It's just being, you can use that for debugging. It'll tell you that it accepted those values. Here's where we take our picture. We just take the still image for individual snapshots. All right, so now let's get into a service, which is basically just a singleton in Micronaut. So in this case, we're declaring it as a service. You don't have to do this. This is using Micronaut's GORM data services. So you don't need to make this an abstract class if you're not using any kind of database access, and you don't need to declare this as a service. You can, if you're not doing any database stuff, you can say this is a singleton, and then just make that a regular class called vehicle service. So what this does is initialize database stuff. It'll actually make your car start faster as well if you do that. I've got a bunch of values that I found for this car that are, these are PWM values and frequencies that I found are the border points where the motor responds to go forwards or backwards and at what speed and where it stops at. So I've saved all these values here as constants just for your reference. But when it initializes the car, what we do is we init the car and we set a frequency of motor forward and motor stop to make sure it's ready. And that kind of wakes the motor up and makes it ready to receive commands. And we're using this 20 hertz frequency here for the throttle, and we're using 50 hertz for steering. And what we do is we start a drive thread, and it's basically that drive thread's constantly looking for a queue to empty out of commands that we're sending it from the front end. I'll show you that here. Before I get to that point, I'll show you how it takes pictures using the JR PyCam library. We do have to disable the camera while we're in autopilot mode because TensorFlow needs access to that. So we turn that off if we're in self-driving mode. If not, we turn it back on. And that's what all this code is here to handle that. And then we basically just take a still image of a certain width and height. This is what the DonkeyCar guys use for their project, and that's what it's expecting this images to be of that size. So that's what we just went with. You can play around with this and make the images bigger if you want and give you a little more resolution. And then we just take this still, and then we write that back out, and then we're streaming that back via Micronaut to the front end. All right, so here's a drive thread that's running, and we're basically, what we're doing is we're trying to create a queue and feed whether we're trying to figure out whether we're going forwards or backwards or stopped in the car itself. And that's basically when you're using that joystick to move around, it's going to give those values, of a gradient between +1 and -1. -1 being full speed backwards, +1 being full speed forwards, 0 being stopped. So we just try to figure that out here and recreate thread if it crashed for some reason. And then we try to figure out what that range is so we can translate that to a pulse width modulation value. Those are simple numbers of gradients, and we can convert that to a pulse. And then we send that pulse to the car saying, go forward or go stop. We're actually using forward for both because the pulse width value for backwards is just a different range of values than forward. So it doesn't really have, the motor doesn't have a concept of going backwards per se, when you're communicating it with pulse width modulation. All right. So here's our queue here, and this is how we switch back and forth between autopilot mode. So if we're going in user mode, we kill the autopilot thread, which is running that Keras stuff in TensorFlow, and then we start up our driving stuff again and reinitialize the motors into a kind of a known state, and then put that in that thread there. And then if we're going in autopilot mode, then we do the opposite here. So if we're doing self-driving mode, we have to turn the camera off, for example, and things like that. And then we're just basically running this autopilot thread here when we're doing self-driving mode. We basically just pass the model name and call this little custom script that Lee made for that. And once that's done, we can show the autopilot started. And at that point, the car is taken over and driving around. Here's how we steer with the Robo4J library. So they were nice enough to build pre-JNI based pre-compiled things. One is you can access the device directly. They also have a higher level API here. So if you're using their framework in its entirety, you can do that. But we're just using one of their classes they're using internally called this PCA 9685 device, which gives you a nice thing. When you initialize it, 50 hertz is the correct value for steering. 20 seems to work very squirrely, so I don't recommend that. And we just tell it what channel we're on. So we're only using 2 channels of this board. Channel 1 we're using for steering, and channel 0 is for throttle. You can hook all kinds of stuff up to this car. We've got 16 channels in total, and we're only using 2 of them. So this is just the beginning of things you could do with it, really. But then we configure a trim value. So you can basically, if your car's slightly offset a little bit to the right or the left, and so dead center isn't dead center for you, you can adjust that in the config file in the Micronaut code, so that whatever's middle for you is middle for it. So it won't just, when you say straight, it's going right or left. That's all you need to do. And one important thing here is we have to pause for a second after we tell the servo to do something to give it time to react. Otherwise, if you don't have the sleep here, the motor won't have time to complete its operations. If you get faster motors or things like that, you can reduce this time. But I found that's about enough to give it enough time to steer to whatever angle you want. Another thing here is we initialize the throttle. We're just setting an initialization frequency for the PWM. Again, that wakes up the motor to make it ready for us steering or us driving it around and giving it throttle commands. Here's how we go forward. So again, they've made a nice thing in Robo4J. We've got a nice PCA 9685 device, and we just basically tell it we've got a motor and then what channel it's on, and we can set a PWM value of on and off. That's basically how long it runs, and then the car will go forward. We kind of go in spurts as we go when it's in manual driving mode, so it doesn't just fly off out of control. All right, so what we're going to do with this in the future, so this is kind of the beginning of it. And again, we've got all those extra channels left we can do things with. So where's our current phase, which is basically our goal was to do a port of DonkeyCar to the JVM, which we've done. Phase 2 is we're going to switch from Keras and TensorFlow to deep learning for J. We're also talking about maybe doing this in the cloud and doing some computations off car. And if the internet connection is fast enough, we could do that with things like MXNet or things like that running on Google or Amazon to do some of the number crunching for us. That could give us things like object detection and different nicety things that are just kind of impossible in the processor speed of a Raspberry Pi. But here's the link for the Deep Learning for J library. So that's kind of on our next to-do list there. And then phase 3, we're going to add more hardware. So we're talking about adding an accelerometer, give us a little bit better telemetry for the model, improve autopilot for control. We're also talking about adding LiDAR. So the Robo4J guys love the LiDAR stuff. We could use that as a local mechanism to detect if something's in the way, like a cat. While we were testing this, we actually hit my friend's Lee's cat with the car. And the other time it spun out of control like a toddler on Mountain Dew. So having something like a LiDAR is a pretty cool idea to make it not crash into other cars in front of it if it's got more than one car on the track, and then you know, just general avoid objects and things like that. And we'll also try to do some object detection. We probably can't do that on the Pi itself because of processing power. We're looking at doing that kind of off-board, you know, either a local server running or in cloud providers for doing that. We want to do the road sharing. So we've got 2 cars, but if you have 2 of them going at once, there's no guarantee they won't collide into each other and knock them off the track. That's one thing that makes real-life versions of these cars a heck of a lot harder to do, is dealing with all kinds of road sharing and objects that, you know, could possibly avoid or not hit. We're not going to planning on scaling this thing up at all. We're not going to do GPS. GPS doesn't really have enough resolution in a small track to be of any use. And then we're not going to scale this up to a real car, not unless somebody you know, gives us one. But you probably would crash a lot, so I don't think that's a good idea. It's not the point of this project. All right, let's. I've got a little demo video here, so I'll go show you. This was recorded at GreatConf EU, and this is the footage provided by those guys. They had some pretty decent cameras there of the car driving around. So let me just show you this. And I've also got a link here if it's a little too choppy for you. There's a link here in the slides that you can go to on YouTube and play it yourself if it's coming through choppy on our presentation software. So let's fire this thing up. All right, here's the training mode. So that's Soren training it. Just doing a little bit there. So we got the car driving around on its own power here. This is the track we built at University of IT University in Copenhagen. And really, the car is just trying to stay between the white lines. And when you're training it, you're doing the same thing. You're teaching it by driving it between the lines. So the better job you do, the better it goes.
Yeah.
So we made kind of a, you know, off track a little bit to give it, make it a little more challenging. And then here's a problem that we run into. I'll show you at the very end of this. So if lighting, this is why lighting is important. So they had a lot of direct sunlight coming in from above. So when it hits that, it blinds the camera. So the camera is basically seeing nothing but white at that point. So then it can't go forwards and it just stops. All right, I just want to give a special thanks out to everyone who helped. Lee Fox, who worked on all this stuff with me. Todd Higgins helped us out with some the hardware stuff. He was an RC car guy. Charles Grossman helped me with the UI. Justin Howe helped us with a bunch of images, and especially thanks to the Robo4j team who helped me out with debugging, having some broken hardware, and they helped me figure that out. Marcus Hurt and Mira Wegner, great guys. Definitely take a look at their stuff if you want to make robots. Here's some resources here that I've got. So this is everything we used. Here's the source code for the car, this Micronaut website, the DonkeyCar website, the Robo4j, Deep Learning4j, where all these autopilot stuff came from, and explain how that works. Here's an article someone did on opensource.com on the car. Maybe I did that. Yeah, I did that. And here's some proper image credits for some of the images that we ripped there of who made them. All right, so we can do some chat questions now if we've got time. If you do, you can get a hold of me here, and then here's a QR code to the deck as well. Link to the deck and a link to the code itself as well on GitHub.
So Ryan, yeah, we had a question earlier that somebody asked if everything was tied to the same ground.
For the car, yes. They're all of the motors, at least, and servos are all wired to that PWM controller, and that's including the ground and power being provided, except for the batteries. So the Pi is running on a separate battery than the car itself. Just because of the stability concerns, the Pi does not like large draws taking away its power. So the car itself's got a separate battery pack from the Pi. As far as signaling, they're all on the same ground, but not as far as batteries. Do we have any other ones?
Yep. And then Jordan had a question and was wondering if you could talk more about how you would train, test, and implement the deep learning model to take evasive maneuvers when a cat collision is detected.
Yeah, so that's basically adding object detection in the mix. That would be additional layers on top of that. So as far as training, the model would have to be enhanced to include object detection layers, and then you'd have to obviously train it with setting up some scenarios of it avoiding things. You may need a little motorized fake cat or something to go across the track to make it learn to detect these things. There's an API available actually that you can do in the cloud things. The problem is the computation power is not awesome on a Pi, obviously. People are using CUDA cores for, like that NVIDIA car, for example, has a whole trunk full of CUDA cores to be able to process stuff like that in real time. It takes a lot of power to do that. But there is potential to have sort of a goal-oriented thing using a machine learning cloud implementation where we say, okay, send us a picture real quick, and it can send back something relatively quickly to say what that even is. We could use LiDAR to just detect an object outside of the machine learning part and just put that in the mix. But the APIs for these cloud providers that could do that, like things like MXNet on Amazon or TensorFlow, basically being done on Google, could give us actual detecting the object and even tell us what it is. So then at that point we could say cat, or stop, or if it's a stop sign, stop, or slow down if it's a yellow triangle, things like that. So that's the kind of things that we're looking to see if we can take this in the future.
Cool. So the PlayStation controller you're using, somebody was wondering, is it connected to the web server or is it connected directly to the car?
It's connected directly to the web server is running on the car, but it's actually connected via Bluetooth to directly to Linux. So since we've got Linux running on the Pi, and we pair the Bluetooth controller, and it just so happens there's a nice driver for that someone made. It was nice enough to make for the Pi on Linux for a PlayStation 3 controller. So you can pair it with that, and then you just access it as a device, basically, to read what it's doing. And that's what the the code itself does for the Python. We didn't really port the training part of it because it's only used really once. So you're really still using the old DonkeyCar training stuff, unless you're actually running the car with Micronaut.
All right. So that is all the questions that are in the chat right now. So if anybody has any other questions, now would be a good time to put them in there. As a reminder, it came through a couple times, but we did record the session today. So we'll send that out to everybody, as well as a PDF of the materials. But as you can see up there on the screen, Ryan's got a link to the deck and the code. And if you just scan that QR code up there on the screen, that'll take you to that as well. Somebody is saying that the link right there is, they can't access it. It's not valid. But if you scan the QR code, it should take you to the materials as well. But we will go ahead and send a PDF out when we send out the recording to the video too. So thanks everybody for joining us. We hope you enjoyed the talk today, and join us for the next one. And we have that coming up next month. All right. Thanks everybody.
Thank you, everyone. Thanks for coming.